our warm-up. So our warm-up asked us first off to prove that the second to last term is equal to n. So I gave you a hint. That means you are proving n combinations of n minus 1 is equal to n. The reason this is n minus 1 is the last term is always n combinations of n, so those end up being the same. If I go one further, or one previous to that, you get to n minus first one. Okay, now again, just like we did in the warm-up, we're just plugging into here. So n combinations of n minus 1 equal to n stayed n. The r place was replaced with an n minus 1. So this is n minus 1 factorial. And then in parentheses it goes n minus r, which is n minus 1. So n minus, now when you subtract a binomial, it technically goes in parentheses because you got to distribute a negative. Now this looks significantly more complicated than what we did, but it simplifies down really quick to look a lot like the proof we have in our notes. Top is n factorial. This part for now stays n minus 1 factorial. N minus 1 becomes n minus n plus 1 in parentheses factorial. The n's cancel out in that parentheses. And I end up with 1 factorial there. What is 1 factorial? 1. Now, when you're trying to prove that one of the terms is equal to n, you've got a slightly different approach on how things cancel out, because you do want things to cancel out. And that is that you have to remember that a term, a number, is always the multiplication of all the numbers smaller than it in a factorial, which means n factorial is n times n minus 1 times n minus 2, etc. And the n minus 1 factorial that we have starts at n minus 1, but then multiplies by n minus 2, multiplies by n minus 3, etc. This right here is the same as this. Therefore, n factorial can always be written as n times n minus 1 factorial. So that's what we do to the numerator when we have the n and the n minus 1s. We break them apart. That's 1. It's no longer needed. N minus 1 factorials cancel out. I'm left with n combinations of n minus 1 being equal to n. As I mentioned on Friday, there will be a maximum of 4 different proofs that show up with Pascal's triangle. We've now done 3 of the 4. The only one we haven't done is proving that the last term is equal to 1, which is the one where we're proving n combinations of n is equal to 1. And that one's going to look nearly identical to question 21 from our homework. That one's going to look even closer to question 21 from our homework than this looks to the one in our notes. Okay. The second thing I asked you to do was to expand the following. In other words, go through and actually do the multiplication to figure out what it's equal to. So, let's start here. X plus 1 to the power of 1. Expanded is just x plus 1. It doesn't really do anything. That one's there for the sake of seeing the pattern. X plus... Oh, I think I said x plus 1. I meant to say x plus y. X plus y squared. To square something is to multiply it by itself. If you did not go through and change this to this, Or at very minimum, if you know the pattern of squaring, be careful. It's not just x squared plus y squared. It's x plus y getting multiplied by x plus y, which you FOIL out. Yep. We get x squared plus an xy plus another xy. Those two will combine, plus y squared, and indeed we'll end up with x squared plus 2xy plus y squared. Now x plus y cubed, you're doing the same thing. In all technicality, I could write it as x plus y times x plus y times x plus y. But then when I go through and multiply that out, I would do it in pieces. Haven't I already multiplied 2 of the x plus y's together and know what that is equal to? Yep. So I'm going to pull one of the x plus y's because I still need it, and then change this into that in parentheses. And multiply it out. X times x squared is x cubed. X times 2xy is 2x squared y. X times y squared is x y squared. So first 3, now I need to multiply y through. Y times x is x squared y. Y times 2xy is 2xy squared. Y times y squared is y cubed. Combine my like terms, I get x cubed plus 3 x squared y plus 3 xy squared plus y cubed. Does this look anything remotely like what we did on Friday? Not really, but there is a connection. Grab out Pascal's triangle. If you don't already have it out, you're going to need it. X plus y, quantity to the power of 1 is 1x plus 1y. X plus y, quantity squared, is 1x squared plus 2xy plus 1y squared. And I'm going to emphasize that too as well. X plus y quantity cubed is 1x cubed plus 3x squared plus x squared y plus 3xy squared plus 1y cubed. Anyone see any connection as to why I'm emphasizing the coefficients? They correspond to the row of Pascal's triangle. This one goes 1, 1. This one goes 1, 2, 1. This one goes 1, 3, 3, 1. X plus y to the power of 1 corresponds to the first row. To the power of 2, the second row. To the power of 3, the third row. So, if that is the case, without actually doing the expansion, anyone think they can tell me what x plus y to the power of 5 probably looks like? coefficients will go 1, 5, 10, 10, 5, 1. 1 x to the 5th plus 5. Now look at what happened with the variables. X cubed, x squared, x, no x's. No y's. Y squared, y cubed. What happened to the exponents on the x's? Went down by 1. What happened to the exponents on the y's? Went up by 1. So this one right here is going to be x to the power of 4 y plus 10 x to the power of 3 y to the power of 2 plus, I got another 10 x squared y cubed plus 5 x y to the 4th plus 1 y to the 5th. Heck of a lot shorter than multiplying out x plus y 5 times. So, this is where we're going in section 10.6. Section 10.6 is called the Binomial Theorem. Technically, this is day 1. The binomial theorem is a theorem that is built off of the idea of working with a series in relation to binomials to a power. Specifically, it is a theorem used to expand binomials to some power. Some not as an addition, as in like the word sum, having something. Okay. Now, what makes something a binomial? Two terms. So it's something plus something or something minus something, where those two somethings cannot simply be combined because they're not like terms. So the generic form of a binomial is written as a plus b, and we put it to some power n. Now a could be a number, could be variables, could be both. B, same thing, could be numbers, could be variables, could be both. The only requirement is, first off, that neither a nor b is 0, and neither a nor b is like terms. Now, granted, if they are like terms, can you do the binomial theorem with them? Absolutely. Does it make sense to? Absolutely not. Combine like terms, distribute the exponent, you're good. Way easier. Binomial theorem has the formula. Starts with our sigma, indicating it's a series. From k is equal to 0 to n of n combinations of k times a to the power of n minus k times b to the power of k. This is binomial theorem. Now, in all technicality, we're not going to use the formula for binomial theorem. We're going to use the patterns of binomial theorem because it's a lot easier to understand the patterns than it is to understand the formula itself. The formula itself, the reason I give it to you is to point out a couple of things. First off, to point out that this does have a connection to series. It has that sigma there. Secondly, I point out the theorem to show the fact that it is using combinations. That n is not a variable that changes. That n is always the exponent that the binomial was put to. The k, as you're working with the series, k changes. You plug in 0, you plug in 1, you plug in 2, you plug in 3, etc. until we get to n, indicating that the binomial theorem uses combinations that will work something like, if n was 5, it would go through and it would be 5 combinations of 0, 5 combinations of 1, 5 combinations of 2, 5 combinations of 3, 5 combinations of 4, and 5 combinations of 5. That's what the combinations that would go into this series would be. That is why Pascal's triangle works so nicely, is because this is the organization of the 5th row of Pascal's triangle as well. I also point out this formula because of the fact that it indicates that the first term, if k is 0, the first term of the binomial, that a, starts as being the power of n and decreases every single time, while the second term, which starts as a power of 0, increases by 1 every single time. It builds and shows you the patterns. That's why I show the formula, and the second reason has to do with what we're going to do tomorrow with the binomial theorem. But today, with the binomial theorem, all you're going to be asked to do is to expand. Now for this first problem, I'm going to write out my example. I'm going to write a bunch of things around it, and then we're going to actually do the actual math for it, because some of you probably caught on to the pattern of what you're supposed to do real quickly based on the warm-up. Some are still like, where did those numbers come from? How did we get x plus y to the power of 5 without doing any math? And so, to meet everyone where they're at, our first example, x plus 3 to the power of 6. So, when it comes to doing this, the first thing you're going to look at is you're going to look up at that exponent. That is going to tell you which row of Pascal's triangle to look at. Can't call in someone who wasn't here. Can't call in someone who's currently not here. Caitlin, what is the 6th row of Pascal's triangle?
1, 6, 15, 20, 15, 16.
You. Now, I recommend that as you're getting used to using Pascal's triangle, I recommend writing this out. Once you've gotten in the habit of knowing what you're doing, you don't necessarily have to, unless you are a person who will lose track of where you are. If you know yourself well enough to know that you lose track of things, always write that down. Okay. Now, from there, the next thing you need to know is you need to know that this first piece is going to start to the power of the exponent and decrease. The second term, on the other hand, is going to start to the power of 0. And increase. Now you're going to want a calculator. If you don't have one, you should probably grab one. So, now that we have those 3 things written out, the process that you're going to go through. as you go through and write out the terms, you're going to grab a Pascal's number, work with the first term, work with the second term, add. Pascal's number, first term, second term, add. Pascal's number, first term, second term, add. That is the pattern that you go through. So, to start this off, the first Pascal's number is the number 1. In all technicality, do you probably have to write a 1 if you're about to multiply by it? No. Are you going to see me do it through our notes today? Yes, because I found that if people do not follow that pattern closely, it messes with them. So I write down that 1. I also cross it off in my list as I go to make sure I know I used it. A single term is going to have all 3 of these pieces getting multiplied together. So 1 times. Then I go x, because that's the first term here, and it's going to start to the power of the original exponent. The original exponent was 6, so it's x to the 6th power. Okay, I'm still multiplying because I'm still working through those 3 things. Pascal's first term, second term. The second term is the 3. Now you have to be careful with this. If it was x minus 3, it would be a negative 3. The original formula only works with plus signs, which means if it's a minus sign, you're adding the negative. So you've got to bring that negative with. In this case, it's just 3. And that is to the power of 0 to start. Now, granted, that being said, what's anything to the power of 0? 1. Do I technically have to write it? No. Do I find that people tend to lose it at times if I don't write it? Yes. That's why you'll see me write it every time. If you're okay with recognizing that that's going to turn into times 1, you can skip it. So, all 3 of those things, then you need to write the plus sign. And we go back through all 3 of those things again. Pascal's number. The next number of Pascal's row was a 6. Write it down, cross it off. Times. The first term is x. It started to the power of 6 at the first term, and it's going to decrease. 6 decreased by 1. Now to the power of 5. Times. The second term was a 3. It started to the power of 0. Its exponents are going to increase. Again, by 1. 0 decreased or increased by 1? 1 plus. Follow your pattern. Pascal's next number is 15 times. X is now to the power of 4. 3 is now to the power of 2 plus 20 times x to the 3rd times 3 cubed plus 15 times x squared times 3 to the 4th. Now be careful. I often see people accidentally flip back and forth between which one increases and which one decreases. So be careful on which one you're looking at. Plus 6 x to the 1st power times 3 to the 5th power plus 1 times x to the 0th power times 3 to the 6th power. Now we're not quite done. We have to simplify this down yet, but before we simplify this down, I'm going to point out some things that can help you double check that you did things right. First off, did your last term end with 1 being to the first term being to the power of 0 and your last term being to the power of the exponent? It's one thing to double check. The other thing to double check is I want you to look at the exponents in each individual term. 0 and 6, 1 and 5, 4 and 2, 3 and 3, 2 and 4, 1 and 5, 0 and 6. What do each of those pairs have in common? They add up to the exponent. So, the exponents are one of the biggest things that I see as mistakes. The second biggest thing I see as mistakes is people changing these times symbols to plus signs or these plus signs to times. So, make sure. Multiply between the 3 pieces that you need, add to get to the next set of 3. From here, you're just simplifying. My first term turns into 1 times x to the 6th times 1 plus. Yes, you can simplify this more in one step. There's a reason I don't the first time. The next term, 6 gets multiplied by x to the 5th, gets multiplied by 3 to the 1st power is just 3 plus between terms. 15 gets multiplied by x to the 4th power, gets multiplied by 9. Do not multiply the 15 and the 3 before you put the exponent on. PEMDAS, please. Plus 20 gets multiplied by x cubed, gets multiplied by 3 to the 3rd power is 27. Plus 15 times x squared times 3 to the 4th. Y'all got calculators. Plus 6 gets multiplied by x to the 1st, gets multiplied by 3 to the 5th. 243 is 243. Plus 1 gets multiplied by x to the 0th power is just 1. Times 3 to the 6th power? 729. So, make sure you're following PEMDAS in your simplifying. I tend to do the exponents and the multiplication separately because if I don't, that's when I tend to see issues pop up. One times x to the 6th times 1? X to the 6th. Plus 6 times x to the 5th times 3? 18x to the 5th. Plus 15 times x to the 4th times 9? 135x to the 4th. Plus 20 times x cubed times 27? 540x cubed. Plus 1215x squared. Plus 1458x. Plus 729. Expanding these out can be a bit tedious. It's less tedious than multiplying x plus 3 6 times and foiling it, but it can be a little tedious. Things, again, that I see as common mistakes that are things you have to keep an eye on. Make sure you don't mix up your multiplication and your plus signs. Make sure you follow PEMDAS. Do exponents, then do multiplication. Do not lose your plus signs when you simplify it down. And keep an eye on which exponents you're expanding. Now, problems like the next one tend to cause some bigger issues. Two x minus 4 to the power of 5. Jada, which row of Pascal's triangle am I looking at?
The 5th row.
Mm-hmm. Alex, what is that 5th row?
1, 5, 10, 10, 5, 1.
Good. Now, the biggest issue that I see in problems like this one is actually two big issues that I see. First off, when we talk about it being a plus b to the power of n, 2x minus 4, a is the entire 2x. B is the entire negative 4. Now, why am I writing that out? The reason I write that out is when I go to do my expansion, I start with the number from Pascal's triangle, that doesn't change. Then when I go to put 2x to what power would it start to? 5th, because that's the exponent here. I cannot write it like this. This is incorrect. I need parentheses around it. that 2 needs to be put to the power of 5 as well as the x. And then when I do the second piece, that b, which goes to the power of 0, if I write it like this, it is also incorrect. It needs to go in parentheses. The only time it doesn't need parentheses is if it is a single piece, no number and variable mixed. If it's numbers and variables mixed, you need parentheses. And if it's positive. That's why this one didn't require any parentheses. If I put it in parentheses, it wouldn't hurt anything. If I don't put it in parentheses on ones like this, it hurts things. So be careful of that. Okay. That being said, Faith, what's the next piece of it going to look like?
Plus 5 times 2x in parentheses to the 4 times negative 4 in parentheses to the first.
Good. Logan, what's the next piece of it going to look like?
Plus 10 parentheses 2x to the third times parentheses negative 4 to the second.
Good. Jaden, what's the next piece going to look like?
Plus 10 times 2x in parentheses to the second power times negative 4 in parentheses to the third power.
Beautiful. Brooke, what's the next term looking like?
Plus 5 parentheses 2x parentheses to the third, to the first, times parentheses negative 4 parentheses to the third.
That one is to the third.
Oh, to the fourth.
Good. Lauren, what's the next term going to look like?
1 times 2 in parentheses
2x in parentheses.
the power of 0
Good.
times negative 4 in parentheses to the power of 5.
Beautiful. Now, one of the things we discussed on Friday is that Pascal's triangle, each row has one more term than the row number. When you simplify these down, you should never end up with fewer terms than there are numbers in Pascal's triangle. You will not be able to combine anything that's separated by a plus sign. So when you do this, if you notice this is to the power of 5, you should know that your final answer is going to have 6 terms because there's one more number in the row than the row number. Okay, now when it comes to simplifying these down, in all actuality, we got a calculator for a reason. Does calculator know PEMDAS? It doesn't.
These ones should.
All calculators know the order of operations. They do, as long as you put it in right.
Well,
You have to know how to put it in right. So if I want to simplify this down, I can make the calculator do most of the work for me. I can't put variables in. The variables I have to figure out myself, but I can put all the numbers with their parentheses to their powers. So I can do 1 times, in parentheses, 2 to the power of 5. Did it probably need parentheses just as a 2? No. But I'm going to do it anyway. Yes. Negative 4 in parentheses to the power of 0. 32. X is going to be to what power? That was the first term. X had what exponent? 5th. I can make the calculator do the simplify. I have to do the variables. My second term had a 5, had a 2 in parentheses to the 4th power, had a negative 4 in parentheses to the 1st power. I get negative 320. Do not write plus a negative. Adding a negative is just subtracting. 320. X would be to what power? The fourth. My next term. 10. 2 to the power of 3. Negative 4 to the power of 2. 1,280. It's positive, so plus. Do not forget your plus and or minus signs. X is going to be to what power? 3. At this point, I could ignore it up here and just look at the pattern. It was 5, it was 4, it was 3. What's it going to do? Decrease by 1. Next term, 10 times 2 to the power of 2. Not minus, times negative 4 to the power of 3. Negative. So minus 2,560. X squared. 5 times 2 to the first power times negative 4 to the power of 4. Positive 2,560 again. This time's just going to be x. My last term, 1 times 2 to the power of 0. I can skip putting that in if I know what it is. Times negative 4 to the power of 5. Minus 1,024. Do you notice that from term to term it goes back and forth from positive to negative? If this is a negative right here, it should. Or if the first term's negative and the second term is positive, it should go back and forth between positive and negative. Using the calculator make it a lot less scary. Yeah. It's a bit tedious if you do it all by hand. Is it doable? Yes. Is it a pain in the butt? Yes. Okay. I'm going to go to my name cards a bit more. Gabby, where am I looking at Pascal's triangle? What are the numbers there?
1, 3, 3, 1.
Good. Leaf. When I go to expand this out, what's the first term going to look like with before it's simplified? It's a 4x.
Or 1 times 4x. To the third. Minus plus 3
Times
times
negative 3y to the power of?
0.
Yep. And you absolutely need parentheses. Where do I need parentheses on this one?
Around the negative 3.
Around the negative 3y and around the 4x. Isabella, what about the second term?
3 times parentheses 4x parentheses to the power of 2 times parentheses negative 3y parentheses to the power of 1.
Addie, next term.
3 times the quantity of 4 to the first power times the
Don't forget to put your variables. Shelby, what about the last term?
1 parentheses 4x to the 0
Okay.
times parentheses negative 3y to the third.
Okay, there's something that we're missing in all of these. What goes between them?
Addition sign.
Plus. Okay, so we simplify down individual terms. This first term, 1 times 4x to the third times negative 3y to the 0th. Elsa, what's that going to simplify down to? Mm-hmm. There's no y on that one? No, you had it right. There is no y because that is to the power of 0, and anything to the power of 0, including variables, becomes the number 1. Bryn. What's the second term going to simplify down to? Yep.
Negative 144 x to the second power and then y.
Perfect. Lainey, what about our third term?
108x 1
Plus 108 x to the first, or just x, y squared. John, what about the last term? Huh?
Negative 3 cubed, so
Negative 27y cubed. There's no x's on that one? No.
to the 0.
It's to the 0th power. Okay. The last one is the one I hand off to you. Expand it out, and I'll give you the assignment.